Hello everyone, I'm honored to speak here. Today I will introduce you a paper which is called an analytical model of MANET single-pass and multi-pass load balancing routing protocol based on Markov model. In this paper, a new analytical model is presented to assess and compare the superiority of multi-pass algorithm over single-pass algorithm in self-organization networks. Okay, let me introduce the background at first. Mobile ad hoc network is a special kind of network that combines mobile communication and computer networks. It doesn't need to rely on a fixed network architecture. The complexity of wireless links is much lower than that of word links, thus making it easier to cause network congestion and reduce network performance, which is the biggest challenge in mobile self-organization networks. To cope with these problems, a series of routing algorithms have been developed for network communication to improve the performance. But different routing protocols have different advantages and disadvantages. Compared with the single-pass algorithm, the multi-pass algorithm has many advantages in the fault tolerance, routing relatable QoS routing. In this paper, a new resolution model based on finite Markov model is proposed for exciting multi-pass and single-pass algorithms based on energy and hop selection factors, and the advantage and disadvantage of single-pass and multi-pass algorithms in various communication or process in four aspects: energy consumption, stability, probability, throughput, and delay. The second part is the research of this paper. Patrick proposed a TLB-LMDV protocol. This method uses the quickness and hop count as metrics for path selection. The quickness field is added to the REQ packet that carried the total quickness that the path passes through. After performing path selection by comparing the buffer size on the path, that is the distribution equally along the path to distribute the load among the paths. Bannis proposed a new protocol called congestion-aware Fibonacci peak-based multiple-path routing protocol. Multiple paths are sorted at the routing discovery node according to the round-trip time of packet requests and replies, and packets are distributed according to the Fibonacci sequence number by assigning different Fibonacci numbers, from smallest to largest in order of round-trip time size. A CBMLB protocol is proposed to use a new parameter to measure network centrality based on channel business. The channel business is defined as a radius of channel where busy time plus transmission time to upper line channel where busy time plus transmission time plus idle time. Two fields are added to REQ and RAP. Each node writes down its channel busy radio in the packet path to the destination and source node and choose the smallest sum of busy for transmission. The next part is the nexus model and load balancing model. The figure shows a random network topology model where node S and node D want to communicate and there are n paths from source node S to destination node D. These paths are considered to be disjoint paths. Most of the pairwise routing models only consider a part of the factor that affect delivery of data packet. For example, only a single factor, such as the number of hops, is considered, and the energy consumption and the routing selection during the data transmission process are not considered. In this paper, we proposed a new analytical model that takes into account the residual energy and the hop count to set up the path selection factor, and the packet sending path is selected by the English Markov model. The summary of parameters used in the chapter is given in this table. We define the energy consumed by sending a data packet as Fc. The potential energy lost by sending a data packet is expressed as FL. The loss energy fit a Bernoulli distribution with probability lambda and the loss energy is EL. We are using formula 1 to conclude the number of hops of path I. In formula 2, assuming that this day there are D packets waiting to be sent during a transmission from S to D. The packets sent each path are Di. The residual energy of the S path is defined as follows 3 and 4. The path selection factor is defined as 5. We define a path selection factor and proved that this model conformed to the path selection model of the finite Markov chains as shown in the equation 6 and 7. The probability of choosing the J's path is 8. According to the above definition, we compare performance in 4 aspects: energy consumption, stable probability, throughput, and delay, and give the corresponding proof as follows. For energy consumption, the single path selects the piece of a path for transmission, and the energy consumption is concluded as 9. The S path on the multi-path consume energy as 10. From equation 9 and 10, without considering the occurrence of congestion, it can be concluded that each path in the multi-path algorithm consumes less energy for transmission than the single-path algorithm. For stable probability is defined as the probability of successfully completing a data transfer process without interruption, assuming that the probability of damage for each node is P. The single-path algorithm selects the T's path for data transmission, and the probability of stability of the single path algorithm is MS. Using multi-algorithm for data transmission, the stable probability is MM. Using mathematical induction for proof, we can prove equation 14. The multiples are more stable than single pass, and it is difficult to interrupt data transmission. For throughout, assuming that during the transmission process, as long as the path doesn't break down, it will continue to send data packet until the path energy is exhausted. You assume that each packet has the same size, then throughout can be expressed as THS and THM. It can be shown multi-pass algorithms have better throughput than single-pass algorithms. In the same situation, the multi-pass algorithm can send more data than the single-pass algorithm. For delay, the data transmission delay is related to the processing power of the node and the number of node hops. There are D data packets waiting to be transmitted during one transmission. Single pass and multi-pass delay is concluded as TS and TM. If the same packet are sent without regard to blocking, the multi-pass algorithm transmission delay is less than the single-pass algorithm transmission delay. The fourth part is a simulation result. The above model is simulation use MATLAB and four metrics for compare. Performance were defined as follows. Energy consumption, the amount of energy consumed to execute a completed transmission process. Stable probability is the probability of success complete a data transfer process without interruption. Throughput is the number of packets that can be sent if energy is depleted. Delay is the time required to send a set of data packets. The value of the simulation parameters are defined in the table. In order to compare the energy of the two different algorithms during data transmission, we suppose that during a transmission from the source node S to the destination node D, the number of data packets waiting to be transmitted is gradually increased from 0 to 500. Figure 1 shows the different energy concentration of the two algorithms. It can be seen that the number of data packets is small. The required energy gradually increased, and the difference is not very obvious from the simulation result. When the number of packets increased, it is obvious that energy required for a single pass rises rapidly, while the multi-pass have finished sending the data, and the energy required on each path will be much less than the energy required on a single path. It avoids that situation that the transmission can't be completed due to insufficient energy. In order to compare the observability of the single-pass algorithm and the multiple algorithm, we sum a damage probability of 0.2 for a single node for simulation experiment. From the figure, it can be the multi-pass routing protocol are more stable than single-pass routing protocol. It can complete a data transmission more smoothly with being interpreted. The analytical energy value of 200 is the seed for each node and is gradually incrementally by 10. The throughout of the single-pass algorithm and the multi-pass algorithm are shown in Figure 3. The graph shows that the throughout of the multi-pass algorithm grows faster than the single-pass algorithm as the energy value gets longer. The difference between the throughout of the multi-pass algorithm and the single pass getting larger. In our experiment, we gradually increase the packet from 0 to 500 and then come to test the propagation delay, and the delay results are shown in the Figure 4. The figure shows that for the same amount of data sent, the multi-pass routing protocol have a smaller delay than the single-pass routing protocol. The fifth part is a conclusion. This paper addressed the performance of multi-pass routing protocol and single-pass routing protocol. The random and the perceivable energy loss during transmission are considered, and the path selection is established in the form of a finite Markov model with the residual energy and the number of path hops as a selection considered. The formatic in single-pass and multi-pass data transmission are analyzed and the simulation experiment, and the experiment result prove that the multi-routing protocol performance is better than the single-pass routing protocol performance. While the research in the future will focus on the path congestion and the impact of link coupling on the performance. Thanks for your listening.